All right, so day 5, sampling distribution for proportions. We've talked about before that a way to remember statistic has to do with the sample is because they both start with an S. And a parameter is a number that describes a characteristic of a population. P and P. That's the way to try to remember those two. Now, the sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size in the same population. So for example, we asked 50 kids at a high school. They all answered. Are the rules on sugar drinks too much? 80% said yes, 20% said no. There are 50 students total. Well, that means 40 of them said yes, and 20 of them said no. What would happen if we only asked 5 students? Well, if we only asked 5 students, so if you think about it, if we got 4 yeses and 1 no, well, that's 80% and 20%. But there's a good chance with only asking 5 kids and there's 40 yeses, there's a good chance we might get 5 yes and 0 no, which is 100% and 0%. So just being different by 1 person in such a small sample changes 80%. It's kind of like a quiz. If you had a 5-point quiz and you got a 4 out of 5, you're already down to an 80. And let's say it was 3 yeses and 2 nos. Not as likely, but you know, that's 60% and 40%. Now, let's say we went up to 10 people. Okay? A little bigger sample. Let's say we got 7 yeses and 3 nos. Well, that's 70% and 30%. But if we had, 6 yeses and 4 nos, again, we're already at 60% and 40%. Now, going up to 20. Let's say we had 16 yeses and 4 nos. Okay, well, 16 divided by 20, that's your 80% right there. So what happens is basically, as you increase the sample size, you're getting closer to the true representation of what happened. So the sampling distributions are very incomplete because they don't have every single combination of sizes, 5, 10, and 20. However, if we were to continue, all 3 distributions, I've had a little trouble speaking today, distributions look fairly symmetric and bell-shaped. In fact, the sampling distribution of a proportion will be approximately normal under certain conditions. And we're going to find that out now. All right. So, first serve percentage. Last year, Kai had a first serve percentage of 53%. He worked with the coach over the summer on his serving. Out of his first 60 attempts, he hit the box 70% of the time. So he improved 17% on his first serve percentage. He used a sampling distribution simulation with a parameter of 0.53, okay, percentage, and N of 60 to see if Kai's serving really did improve over the summer or if he just started this year better. So what we have here is we have a sample, this is a simulation, a sample proportion of successful first serves. It's pretty symmetrical, pretty bell-shaped, and here's the 0.70 that he hit. Okay, well, the population is going to be all serves from last year, or previous. Okay? The parameter is at 53%. Remember, we said it's a number. The sample is 60. And the statistic that we're using is the 70% that he hit. Okay? Now, the 70% that he hit was only 1 out of 60 simulations. Pretty high up. Okay? So, what that tells us is 1 out of 60 is a pretty slim chance. So, that says that the coaching must have had a positive influence, because the likelihood of it not having an influence would not have had him up that high. Okay? So it's against common sense to think that the coaching had no influence to go up that high, since 70 is so far to the right, it's almost an outlier in terms of the rest of it. Now, what does 0.37 represent? Well, that's one serve, of 37% first serves in. I meant first serves. So first serve, 37% in the box. Okay, so that would be the worst case scenario. So this normal distribution went anywhere from 37 to 70% in the simulation. This also only had a 1 out of 60 chance. So if it was just blind luck and the coaching had nothing to do with it, he could have had a 37% chance in the box. But he didn't. He had 70. Okay, what does the mean and standard deviation? Well, it looks like the mean is probably about 53% right there. And that makes sense, because that's what the overall average was last year. Now, what do we think the standard deviation is? Let's look at that. Okay, first off, I lied. I wasn't thinking. The simulation has way more than 60. It's more like the simulation actually has about 200 actual dots on there. So the chances are actually 1 out of 200 that it would be 70%. So even more so, coaching had something to do with it. Now, standard deviation. 68% of it should be in the middle. So that means +1 and -1 would be right there. So if we're going from 53% to 60%, that is about 7%. So the standard deviation, 7%. So, or 0.53 and 0.07 on the chart. All right, and moving on. Based on simulation with a P of 0.53 and N of 60, is it possible Kai improved over the summer and P is greater than 0.53? Well, considering how far greater 70% is compared to 0.53, there is a good chance of that. Because when he actually hit 70% on his first serve in the box was way far off to the right. That was an extreme number. All right, so we're going to go to this website, which I already have pulled up. Actually, I'll just go here now. Okay, and we have the Reese's Challenge. I'll move this over here. Okay, so I'm just going to do this. You just have to watch real quick. Don't worry about it. So notice it says we're doing the probability of orange. Okay, we're looking at 25 candies being dispensed down here. So what I'm going to do is, it says number 1, click on it, which you did, and it says proportion of our orange. So I'm going to change that here. And it says on number 3, click draw, on number 2, draw samples. So there we go. It's getting oranges and other colors out, and it was at 0.48. Probability is 0.5. So was that pretty close? Yes, it was. and it's going to put that dot on the chart down there. Now, it says do this 9 more times, and I'm going to do this real quick. Okay, and it's going to spin those out. That's going to give me the most recent there, but you can see the breakdown there. Okay, that is 10 tries. Now, is it symmetrical? No. If you look at that, it looks like kind of like the left side of the symmetrical of the bell curve, and that 0.5 there is actually, starting on the right side. So if I look at that, that is not symmetrical, and looking at expecting 0.5, it looks like more than the left half. Now, for number 4, it says to make many more, we're going to enter the 990 in the number of samples. So I'll put that in. And I'm going to take off the animation so it doesn't have to animate every time. Now watch. Boom. There is 1,000 samples. Now, what do we have? Does it look pretty symmetrical? Yes, it does. What's the highest number? 0.5. Or in that area around 0.5. So, it is very symmetrical. Okay? Now, for number 5, it says, how does the shape of the sampling distribution of p hat, we call it p hat, change if the proportion of orange candies is 10% instead of 50%? So let's do that. I'm going to change that to 0.1. And we're going to do 1,000. Now, if you look at, 10%, our highest is at 8%. It looks fairly symmetrical. It's a little bit skewed to the right. There are some outliers out there to the right, 0.32. But if we took off 0.32 and maybe even 0.28, it is pretty close to symmetrical. And we're going to do one last change. It says on number 6, how does the shape of the sample distribution of p hat change if the sample size increases? So we're going to set the probability to 90%. And we're going to draw 1,000 samples. Then we're going to repeat with 100 and 500 and see how that affects the shape of the distribution. So just watch. So here's 1,000. Then 100. And 500. It's hard telling at that amount because 500 is already a large amount. They're pretty symmetrical. There is some skewage. This time it's skewed a little bit to the left. But the larger the number, the more representation you're going to have in a normal distribution.